This is the screencast for section 9.4, example 4. We're going to find the limits of these particular sequences. And then if the sequence converges, we need to give the limit. So we have to find whether or not each of these sequences has a limit. So I'll take the limit of each one. And just like the last example, I want to remind you that 2.6 examples 3 through 9 will give you help on rational function end behavior. I mean, these are rational functions. We're just using specific entries along their graph to define a sequence. So if you study the rules for the end behavior of rational functions from section 2.6, it'll help you take the limits a little bit more easily. In this first one, part A, the degree in the numerator and denominator are the same. So the limit will equal the leading coefficients, which would be 3. So this sequence defined by 3n over n plus 1 converges to 3. Part B, the degree in the denominator is higher, so this limit will equal 0, which means this sequence converges to 0. And part C, the degree in the numerator is higher, so the limit as n approaches infinity would be infinity, and therefore this sequence defined by n cubed plus 2 over n squared plus n diverges. Then now try problem number 15, says determine whether the sequence converges or diverges. If it converges, give the limit. So we need to take the limit first to find out if it converges or diverges. Now this one, the degree in the numerator and denominator are the same. If you want to rewrite this to have the leading coefficients out in front to more easily see them, you're more than welcome. So the limit as n approaches infinity of this sequence would be -1, so 3 over -3. So this converges to -1.